Hi everyone. So in this video I would like to go over how we have those kinematic equations, especially how we derive the four equations we are going to use for constant acceleration motion. So we have learned two different cases, two special cases of motion. One is uniform motion. Another one is constant acceleration motion. So what would be the difference between them? So if we would like to plot the acceleration versus time plot, what is it look like for uniform motion and constant acceleration motion? So for constant acceleration motion, of course, then you have your acceleration is constant. Now if your acceleration is constant, you should have your velocity goes up linearly, and this would be your initial velocity at time t equals 0. Here t equals t0, and then you will have your final velocity tf. This is your final velocity, and the slope will give you your acceleration, and your slope should be expressed as vf subtract the initial velocity over time interval tf subtract t0. There's constant acceleration motion. Now the position versus time plot for constant acceleration should be a quadratic curve, parabolic. Now let's go to uniform motion. Now for uniform motion, it's also called constant velocity motion, which means velocity doesn't change. Now if velocity doesn't change, which means your acceleration is always 0. So your acceleration has to be 0 all the time for uniform motion. And then from the name, uniform motion, constant velocity motion, so your velocity is always a constant over time. So for any given time, velocity equals to this initial velocity. And then if your velocity is constant, then on a position versus time plot, your position should go as a straight line, and this is your initial position, this is your final position, this is t0, this is tf, and then the slope. The slope should give you velocity, which is final position subtract initial position over time. So put them side by side, we should notice the difference. Acceleration, for uniform motion, acceleration is always 0. For constant acceleration motion, acceleration is always a constant. Velocity for uniform motion is a constant. Velocity for constant acceleration motion is linearly increasing over time. Okay. Now let's have a look at this example for constant acceleration motion, and for us to appreciate the fact that if you have velocity versus time plot, this should be 1, 2, 3, 4, 5. Then the area and velocity versus time plot should give you displacement. Now let's check out the velocity versus time plot from 0 to 1. Let's look at this area. So we know the displacement for constant velocity motion should be given by velocity times time. So this is the velocity times the time interval, which exactly give you the displacement. So the area under here should give you the displacement from 0 second to 1 second. So this displacement is 2 meters now. And let's check this area. This area is 2 meters. And even the unit works, you see. The unit for velocity is meter per second times 1 second. This is 1 second. So meter per second times second give you a meter. So the area of this area is 2 meters. Now same for this one. If you check out the area here, is velocity is 1/2 meter per second, and time interval is 4 seconds. So this time interval 4 seconds, and you find that the area is also 2 meters. So let's check out the displacement from 1 second to 5 seconds. The displacement is from 2 to 4. Displacement is also 2. Displacement is 2 from 0 to 1. So basically, we kind of see that for uniform motion, the area of a velocity versus time plot, the area under the velocity versus time plot give you displacement. And actually this is generally true. So even if it's not uniform motion, is arbitrary kind of motion, you just cut it into another rectangle. So you see for each of the rectangle you have, so you can approximate the velocity as a constant. So velocity times this time interval give you displacement in this very tiny time interval. So as long as you cut the squares small enough, you sum everything up. If you cut them small enough, this means you need to cut them small enough, and then you sum everything up. You have the area under this curve. You have the net area under this curve, and it should give you the displacement from T1 to T2. But if you have learned the calculus, you should know this one gives you nothing but integration Okay, if you haven't learned calculus, don't worry. There's nothing you need to worry about here. Just you need to understand displacement, the area under velocity versus time plot, area under velocity versus time plot gives you displacement. Okay, we're going to use this one to derive the equations, kinematic equations for constant acceleration motion. So suppose we know the initial velocity of the object is v0 at t0, and the time interval is t. We just write it as t. So final time subtract initial time, we know it as t. So we know the constant acceleration motion final velocity equals initial velocity plus at. This is also, you see, this is also definition of A. Final velocity subtract the initial velocity over time interval give you A. So this is the same equation. This is the first equation of constant acceleration motion. So let's write this down. The first equation of kinematic equation for constant acceleration v0 plus at, and we can have a plot for this t v. So at t equals 0 it's v0. Okay, so after time, so after time interval, its velocity is v, final velocity is v. V is v0 plus at, depends how long it elapses. Now we want to use, first we note this one as a first kinematic equation. So we want to use a fact, a very simple geometric fact. So you can check out this, the area under this curve is a special shape in geometry, trapezoid. So this side is v0, this side is v, and this side is t. And then we should know how to calculate the area of this trapezoid. The area and I highlighted should be 1/2 v0 plus v times t, right? So this is just a very simple geometry fact. And what is this? The physical meaning of this area? This is velocity versus time plot. Because the area under this curve gives you displacement. So quickly we get our second equation. So displacement equals 1/2 v0 plus vt. 1/2 initial velocity plus final velocity times t. So this 1/2 v0 plus v can also be reinterpreted as average velocity, or you can write it as average velocity for this motion. So for constant acceleration, actually the average velocity for time interval is initial velocity plus final velocity over 2. Okay, now we got two equations already, which is pretty good. Now we're ready to move on. We can easily get our third equation, use equation 1 and equation 2. So what do? I will replace v in equation 2 by the right hand side of equation 1. Because v from equation 1, v equals v0 plus at. So I have displacement equals 1/2 v0 plus, okay, v equals, I want to write v as v0 plus at times t. Now if you carry it out, you should have v0t plus 1/2 at squared. This is our third kinematic equation. Now the fourth one, which I also always say that's my favorite one, that you need to solve for t from equation 1. T equals final velocity subtract initial velocity over a. Then you replace t in the second equation here by this one, which will give you the fourth equation. So you will have that x equal 1/2 v0 plus v times v subtract v0 over a. Now if you make a neat bit rearrangement, you should have 2a that x v squared subtract v0 squared. So let's examine it. So in total we have 5 variables in these 4 equations. 5 variables, which are final velocity, initial velocity, acceleration, t, and displacement. Now, if you check it again, equation 1, 2, 3, 4, each of them only contains 4 variables. So if you know 3 variables out of these 5 variables, you are able to solve for the unknown quantity, and this is how we are going to use those equations. So the problem solving strategies should be you need to write down the known quantities where always needs to give you at least 3, and then you need to write down the quantities that the problem is asking for. So you have 4 quantities, 3 known quantity, 1 unknown. Then you need to check which equation that I just showed you contains those 4 quantities, 3 known and 1 unknown, and then use your simple algebra to solve it. So a very simple example. The takeoff speed of airplane is 360 km per hour. And if its average acceleration is 2.4 meter per second, how much time is it accelerating down the hallway before it lifts off? So of course, first of all, we write down the known quantity. It gives us final velocity is 360 km per hour, and accelerating down the runway, so it also inexplicitly gives us initial velocity 0 meter per second. It gives us acceleration 2.4 meter per second. So it asks us for the time. So you need to check which equation contains those 4 variables from this one. 1, 2, 3, 4. Which equations contain those 4 variables? So let's check the first one. Final velocity, initial velocity, acceleration t. Actually, ta-da! That's it. That's the equation we should use. Now the catch here, you need to convert this one to meter per second first. So you have 3, 6, 1, 2, 3 meter per second. 1 hour is 2600 second. So in meter per second, this one should give us 100 meter per second. So the airplane has to reach 100 meter per second so it can take off. So we know time from equation 1 should be final velocity subtract initial velocity over a, which is 100 meter per second over 2.4 meter per second square. If you first you work out the unit, you'll find this part should give a second. And okay, now if you work out the numeric part, it's roughly 41 seconds. So 41 seconds. And this is a very simple example to show how we use these kinematic equations. And I'm going to upload a video on more involved complication of those kinematic equations right away.